Video, I'd like to finish chapter 3.3 on counting atoms, and I'll begin by introducing the concept of a counting unit. A counting unit is a unit that we use to specify a certain number of objects or things. For example, one pair is equal to 2 things. A dozen is equal to 12 things. A score is equal to 20 things. So we use these to simplify counting large numbers of things. Now, in chemistry, the counting unit that we use to specify a number of chemical entities, that is atoms or molecules or whatever, is 1 mole. And because chemical entities are really, really small, and macroscopic amounts of them have lots and lots and lots of things in them, this number, 1 mole, is very large. It is 6.022 times 10 to the 23rd things. In this unit, because we are dealing with atoms of elements, the things will be atoms, as you will see in a moment. This is called Avogadro's number, named after the Italian scientist Amedeo Avogadro. Avogadro's number is 6.022 times 10 to the 23rd things per mole. You do not need to memorize that. It will always be given to you, but you probably will memorize it anyway. So let's see how we use Avogadro's number to convert from moles to atoms. Suppose I give you a sample of nitrogen and I tell you that there are 5.69 moles of nitrogen in it. And I want to know how many atoms is that? We will use Avogadro's number as a conversion factor. And here's how you set up the calculation. I'll take my number of moles of nitrogen, 5.69 moles of nitrogen. You can put it over 1 if you want. I know my conversion factor will have to have atoms of nitrogen in the numerator and moles of nitrogen in the denominator. I look at Avogadro's number, and I see that the number that goes with things or atoms is 6.022 times 10 to the 23rd. The number that goes with moles is 1. So I will put 6.022 times 10 to the 23rd atoms of nitrogen in the numerator and 1 mole of nitrogen in the denominator. Moles of nitrogen cancel moles of nitrogen, and rounding to 3 significant figures, I get 3.43 times 10 to the 24th atoms of nitrogen. Suppose I give you a certain number of atoms of phosphorus and I want to know how many moles that is. Well, I can set it up in a similar way. I start by writing down the number of atoms of phosphorus I have in the numerator. Now I want to multiply by a conversion factor that has moles of phosphorus in the numerator and atoms of phosphorus in the denominator. Again, 1 goes with moles, 6.022 times 10 to the 23rd goes with atoms. Atoms of phosphorus cancel atoms of phosphorus, and rounding down to 4 significant figures, I get 114.1 moles of phosphorus. Notice that an acceptable abbreviation for mole is MOL. Another way to perform this calculation looks like this. I can take my atoms of phosphorus, and rather than multiplying by the reciprocal of Avogadro's number, I can simply divide by Avogadro's number. So 6.871 times 10 to the 25th atoms of phosphorus divided by 6.022 times 10 to the 23rd atoms of phosphorus per mole of phosphorus. Mathematically equivalent, atoms cancel atoms, and I get the exact same result. So set it up whichever of those ways makes more sense to you. Now, how is the mass of a sample of an element related to the number of atoms in it? Well, we defined the atomic mass of carbon-12 as exactly 12 unified atomic mass units per atom. But we can use mass spectrometry to measure the mass of 1U in grams, and it is 1.661 times 10 to the negative 24th grams. So let's calculate the mass of 1 atom of carbon-12 in grams. I'll multiply 12U per atom by 1.661 times 10 to the negative 24th grams. U cancels U, and I get a value of 1.993 times 10 to the negative 23rd grams per atom of carbon-12. Now let's use Avogadro's number to calculate the mass of 1 mole of carbon-12 atoms. So I'll take my 1.993 times 10 to the negative 23rd grams per atom, multiply by Avogadro's number of atoms per mole. Atoms cancel, and I get exactly 12.00 grams per mole. 12.00 grams per mole is called the molar mass of carbon-12. The molar mass is defined as the mass in grams of 1 mole of an element, Avogadro's number of atoms. And what we see is that the average atomic mass of an element in U per atom, which we saw up here, is numerically equal to its molar mass in grams per mole, which we saw down here. Okay? They are numerically equal to each other, they simply have different units. So, take-home message is, the number that you see in the bottom of the box in the periodic table is simultaneously the average atomic mass of that element in U per atom and the molar mass in grams per mole. This then gives us a very powerful tool. I can now convert between mass and moles. What is the mass of 8.09 moles of xenon? I will use the molar mass from the periodic table with units of grams per mole as a conversion factor. So I will take my 8.09 moles of xenon over 1 if you like, and I will multiply it by the molar mass of xenon from the periodic table, 131.29 grams of xenon per mole of xenon. Moles of xenon cancel moles of xenon, and I'm left with 1,060 grams of xenon, rounding to 3 significant figures. Suppose I give you a certain mass of sodium and I want to know how many moles are present in it. Well, I can use the molar mass again. I'll start by writing down the mass of sodium. And now I want units of moles of sodium in the numerator, grams of sodium in the denominator. What goes with grams? The molar mass from the periodic table, which is 22.99. What number goes with moles? 1. Once again, grams cancel grams, and I'm left with moles of sodium, which is 21.0 moles of sodium. Again, rather than multiplying by the reciprocal of the molar mass of sodium, I could simply divide that by 22.99 grams of sodium per mole of sodium. Same thing, grams cancel grams, and I get the exact same result. So once again, do it whichever way makes more sense to you. So a question arises, how many sig figs can you use in your molar masses? Well, you have 2 options. You can either use all of the sig figs given on the periodic table. So for example, potassium on the periodic table has a molar mass of 39.0983 grams per mole. Oxygen has a molar mass of 15.9994 grams per mole. That's perfectly fine. Or if you want to round, you can, but always keep at least 4 significant figures and at least 2 digits after the decimal point. In that case, potassium would round to 39.10 grams per mole, and oxygen would round to 16.00 grams per mole. Either of those options is fine. Finally, let's convert between mass and atoms. Here's the final conclusion, how we determine the number of atoms in a sample of an element. Suppose I give you 90.4 grams of iron and I ask you how many atoms are present in that. Do we have a conversion factor that directly relates mass and atoms? No, we don't. So we're going to have to do it with 2 conversion factors. And here's how it works. I'll begin by writing down the mass that I'm given, 90.4 grams of iron. I cannot convert that directly to atoms. The first thing that I can convert it to is moles. So I will put moles of iron in the numerator, grams of iron in the denominator. The number that goes with grams of iron is the molar mass from the periodic table, 55.85. The number that goes with moles is 1. If I were to stop here, grams of iron would cancel grams of iron, and I would have moles of iron. But I want to go one step further to calculate the number of atoms of iron. And to go from moles to atoms, I will use Avogadro's number, 6.022 times 10 to the 23rd atoms of iron over 1 mole of iron to give me my final value of 9.75, running out of space here, sorry, times 10 to the 23rd atoms of iron. So this is how you go from the measured mass of a sample of an element to the actual number of atoms in it. Or in the reverse direction, suppose I give you a certain number of atoms of ruthenium and I want to know how many grams that would be, what's the mass in grams, I would do something similar, but in the reverse direction. I would start by writing down the atoms of ruthenium. I can't go directly from atoms to mass, I can only go from atoms to moles, so I will multiply this by 1 mole of ruthenium over 6.022 times 10 to the 23rd atoms of ruthenium. At this point, I forgot to cancel moles of iron. At this point, atoms of ruthenium cancel atoms of ruthenium, and I have moles of ruthenium. Now I can use the molar mass from the periodic table to convert from moles of ruthenium to grams of ruthenium. So I'll multiply by 101.07 grams of ruthenium per 1 mole of ruthenium. Moles of ruthenium cancel moles of ruthenium, and I get my final result, which is 6,080 grams of ruthenium. Or again, as we saw before, we can simplify this by taking 3.62 times 10 to the 25th atoms of ruthenium, dividing by Avogadro's number, 6.022 times 10 to the 23rd atoms of ruthenium per mole of ruthenium. Atoms cancel atoms. This whole first expression represents moles of ruthenium, so I can simply now multiply that by 101.07 grams of ruthenium per mole of ruthenium. Mole of ruthenium cancels, and I get, just as before, the same result. Once again, do it whichever way makes most sense to you. So, let's summarize. Here's what I expect you to be able to do. Given the mass of an element in grams, convert it to moles of the element. Given moles of an element, convert to atoms using Avogadro's number. And in the other direction, if I give you the certain number of atoms of an element, convert to moles using Avogadro's number. And if I give you a certain number of moles of an element, convert to grams using the molar mass. Here is a little graphic organizer that represents these calculations. If I give you a sample of an element, I can express the quantity of that element in one of 3 ways: the mass in grams, the number of moles in units of moles, and the number of atoms in units of atoms. To go from mass to moles, I divide by the molar mass in grams per mole. To go from moles to mass, I multiply by the molar mass in grams per mole. To go from moles to atoms, I multiply by Avogadro's number in atoms per mole. And to go from atoms to moles, I divide by Avogadro's number in units of atoms per mole as well. Okay? Oh, this is an important point. What do you call 6.022 times 10 to the 23rd avocados? You can see this one coming. It is 1 guacamole. I'm really sorry about that. That's the unit.